Again, as I was saying, today is basically the beginning of the last chapter of this class, chapter 32. I already sent a message earlier in the day basically stating the fact that we have quite a few things to do before the final. The final is going to be on December 14th, that's a Monday, okay? And then exam 4, which is going to be next week on Wednesday. So basically the last contact class that we will have is going to be on Monday, okay, a week from today. So this is where we stand. In terms of labs, the last lab that we're going to have is today about diodes and basically transistors. And that's a lab that did not occur really in the proper place in terms of the sequence because we had to do a few other things before we get into it. So this is the last lab for that. So that's where we stand in terms of everything, what we need to be doing. I'm not done grading with everything, but I'm hoping that since I'm not done, that you guys, especially those who did not submit your assignments from before, you get going and rush and make sure you put things together there, because I saw that these things tend to change the grades a lot. I mean, they fluctuate up and down. So make sure you have all of your assignment turned in. In terms of the discussions, today is going to be the last discussion that is going to be graded again. So that's where we stand on everything else, okay? So I'm gonna share with you this screen, unless you guys have any question. So this is the content for chapter 32. What chapter 32 really is the summary of everything. Okay, we're going to take Maxwell's equations, the ones that we discovered. We're going to revisit them all completely from beginning to the end, and we're going to seek a solution in what is known as free space, meaning that we're far removed from any charges and far removed from any currents. And at that point, the Maxwell's equations themselves becomes a lot easier, because remember, Gauss's law state that the flux of the electric field over closed area depends on the number of charges that are enclosed. But if we are in free space, there are no charges enclosed, so that integral will be 0. Okay? And also Ampere's law said that the fact that the circulation of the magnetic field depends on two things. First of all, it depends on how the electric field changes. If it does, then we have to find the flux of the electric field in that region and find its time derivative. That was a so-called displacement current that Mr. Maxwell had to introduce to correct Ampere's law. But the second part in it deals directly with the current that is enclosed in the path where we're calculating the circulation of the magnetic field. So if there is no currents because we're in free space, that part also is 0. So Maxwell's equations tend to be a lot easier in free space. So this is the whole idea. So we're going to be in free space and rewriting Maxwell's equations in free space. What free space means is that basically two things: no charges. We don't have any charges to worry about. That means that charge density is 0. So the first thing that we're going to say in here is rho is equal to 0. That's what free space means. Imagine with me that an electric field was created by a charge moving. Remember, when charges are accelerating, they emit energy, they radiate energy. They radiate electric fields, actually. That's basically what this whole thing is. And that's how antennas work in actuality, okay? So antennas, transmitting antennas, the way they work is by having charges moving back and forth, oscillating, and because oscillations is one way of finding accelerating charges, so they will emit electric field. So at that point, far from that charge, then we're dealing now with the free space. Okay. A charge also, when it's in motion, it's a current too, so it's going to create a magnetic field. So both E and B are created, but we don't care about them at this point. We're far from where that charge is that does that. So that's what's going on in light bulbs, for example, in any place that radiates or emits energy, that is going to have charges accelerated. Okay, so free space also means there is no current densities. Okay, so those are, or currents, to be more general. Remember, current density J is by definition I over A. area. So this is in amperes per meter squared. That's basically what the current density means. That's how much, just like the charge density, except. So having said that, let's look at Maxwell's first equation. It says basically, I'm going to write it both in integral form and also in differential form. So it says that, Gauss's law that is, it says that the flux of the electric field over a closed area, that's what the circle means in there, is equal to the charge enclosed over epsilon naught. And I know this is 0 in free space. So that's one equation. So this is a Gauss's law, really. It's what I'm saying in here. These are all of Maxwell's equations, and they are the summary of all of these equations put together. The second law says that the flux of the magnetic field over a closed area is 0. This is 0 no matter what, because there are no monopoles. Basically, if I have a magnet, a bar magnet, the field line that leaves the North Pole will ultimately come back and to terminate in the South Pole. So if I take an area, doesn't matter how big it is or how small it is, there is a field line that's going to leave it, but it's going to come from another side. So if I'm counting the field lines for the magnetic field, I will always have one positive and one negative, and they will cancel one another. Now, if I'm in a region when there is really no magnets, period, or there is no currents, period, same thing, by the way, with the currents too. They will always circulate in a sense that if no matter which closed area I will have, it's always going to give me a 0, because the field lines, they're always, for the magnetic field, they rotate, they circulate, basically go around in circles. So if I'm going to have a closed area, no matter how am I going to choose it, either I have no currents inside, which is 0, or I have currents inside, which are going to create field lines that are going to circle around, so they're going to come in and out of my surface. So this is the fact that there are no monopoles. Always I have North Pole and South Pole together. Whereas in the first case, I could end up with positive charges by themselves and negative charges by themselves. And I could calculate the number of charges, and I will end up with a net positive number or a net negative number. But in this situation, it doesn't matter. I'm in free space. In free space, I don't have any charges. I don't have any currents. So both of these integrals are 0. So these are the fluxes. Now the circulation. The circulation of the magnetic field over a closed path, this is Ampere's law, is equal to mu naught times the current enclosed, and I know I'm in free space, so this is 0, plus a term that is Mr. Maxwell introduced to account for the fact that I know we did the example of the condenser, the capacitor, and we have to fix the law so that it works even in that situation, and this is the so-called displacement current. Okay, where this phi E is the flux of the electric field across the through the surface, or a surface enclosed by the path, and I have to put it in capital in here because this integral is over a path, some path in here. So this circulation is along some path, okay? And since I'm calculating through this path, the circulation of the magnetic field, this calculation on the second of the flux has to be through an area enclosed by that same path. Okay, so these two integrals, the boundaries of integration, have to are dependent. In other words, what phi E is really is the integral, and it's an open integral because this doesn't have to be a closed path, of EdA. So that is really what the flux is in this case. So this is Ampere enhanced by Maxwell. but the first term in the second half is 0 because of the fact we are in free space. Okay, so free space dictates that there are no currents. So we are far removed from any source. Source of what? Of both electric and magnetic fields, EM fields. The thing is, Maxwell's equation, the three of them so far are here. There is a fourth one, and that is Faraday Lens Law, and basically that says, always true, that the circulation of the electric field, in this case, which is weird because normally the electric field doesn't circulate, and this is actually what the EMF is equal to minus the changes of the flux of the magnetic field over a closed, over an area that is enclosed by this path. So this integration is over any path. And this also, the flux in this case has to be changing over an area enclosed by the path. Which path? It's this path. So this is time changes of the flux of the B field now through an area, any area actually, enclosed by, again, the path. What I mean by the path is this very same path in here, okay? The same analogy on the other side. So this is basically Maxwell's equation. At this point, we really don't need Lorentz force because we don't have anything in here to worry about. Unless you have a receiving. So think about it this way. So you have a transmitting area that transmits signal. Like it could be an antenna. It could be, for example, a star. It could be your light bulb. It could be anything, as long as it creates this signal. Okay. It could be the station broadcasting next door. Okay. So it has charges that are creating electric fields and magnetic fields, and this field is going at some point traveling in free space. At this point, this is how Maxwell's equations would look like. Okay, at least in integral form. So those are the four Maxwell's equations. Now, once they reach once this electric field and magnetic field reach a receiving point, so I have a receiver now. And of course, if I still have electric field and magnetic field left over, they will interact with charges. Then you're going to invoke Lorentz force. And F equals to ma and all of that. Lorentz force, if you guys remember, QE, vector form of course, plus QV cross B. So at this point, we don't care for it because we are here. We are in the middle of free space. We don't have anything in between them. So we're looking for the electric field and the magnetic field and how they look like. So that's basically in a nutshell how this story is for chapter 32. Do you guys understand where we are really situated in terms of this whole problem? So we took Maxwell's equations, which are valid everywhere. Okay. And I said the following. I said we're going to go in free space. We're going to focus on an area of space where there are no charges to create their own electric fields, and there are no currents to create magnetic fields. Okay, and there are not charges even sitting still to react to this electric field. So at this point, we are in free space, completely empty of anything. There is no matter whatsoever. And now we're going to look at Maxwell's equations and see if they make sense, if they're going to give us something that we can work with. So that's the whole promise of this whole chapter. Okay. So as you can clearly see from my discussion, from the points I'm raising in here, I'm actually headed towards telecommunications. This is basically where this whole thing is at this point. Okay, so let's go back and continue with this thing. Let me rewrite the same equations in differential form because sometimes they are a little bit easier in there. So remember, the double integral, the divergence looks like it's the divergence of the electric field equals, in this case, 0. Normally, it's equal to rho over epsilon naught, but rho in this case is 0 because we're in free space. The divergence of the magnetic field is always 0. That's because there are no monopoles. Okay, the circulation of, that's the curl actually of B, the circulation of the magnetic field in this situation is usually mu0, mu naught J, but this J is equal to 0 because we are in free space again, plus mu naught epsilon naught. Now the time derivative of the electric field actually, and I'm using partials in this case because everything depends potentially, the electric field is a function of both x, y, z, and t. If the magnetic field, also the same thing. It's a function of both x, y, z, and t. They vary in space and time. That's why we cannot use really straight derivatives, because we have to take into account the fact that we're dealing in free space, in multivariable functions, basically. And the last thing that we will need is the circulation of that electric field per Faraday Lens law is minus dB over dt. Okay, so this is how Maxwell's equation is now reduced to in this situation, in the differential form or in integral form. Let me rewrite them, summarize them actually. The circulation, the flux of the electric field is 0 because there are no charges enclosed, because we are no charges, period, we are in free space. The circulation of the magnetic field, the divergence of the magnetic field, I should say, is 0 because there are no monopoles. This is always 0, no matter where you are in space, free space or no free space. And then the last two equations are the circulation of the magnetic field is, did I put a DL? Did I put the correct symbols? Yeah, okay, good. The circulation of the magnetic field is going to be just that displacement current. Oops. We're doing, after we integrate over space, the only thing that is left in this case is the time dependency, okay, of EDA. Because here we're integrating over space, so we're getting rid of any spatial. So this function at the end, once we integrate it over that surface, is going to be just time dependent. So that's why there is no need to do partials in this case. It's straight out derivative with respect to time. And the last integral was Faraday Lens law that says basically the EMF, which is the circulation of the electric field over a closed path, is equal to minus, again, d with respect to dt over BDA. BDA. Again, for the same reason as before, this would become just a straight derivative with respect to time, because you sum up all of the magnetic field and the different points of the area over that area, and at the end, the only thing that you're going to be left with is just a time-dependent factor, so there is no need for partials. So these are the same equations as above, except the last four are written, there are four, by the way, here, are written in integral form, and the same four are local in the given point in space. So what we're going to do is the following. We're going to consider something called the planar solution, see if it makes sense, see if it works or not, okay? So I'm going to add a page in here, and I'm going to find a planar solution, okay? Where can I type in here? What is that? Type. Okay, good. What that solution means is, here is how it looks like. I'm going to assume the following. I'm going to assume that the electric field is only dependent on one variable only in terms of space, but also in terms of time. And the same thing for the magnetic field. So what I'm saying is the following. There is a plane in space that is perpendicular to the x-axis. That's actually in the same direction as the x-axis, whereas the electric field is the same everywhere in this plane. So if you take any point in here, the electric field has the same value. Okay? So this is the x-axis. This is the y-axis. And this is the z-axis. Okay? X, Y, Z. Okay? So this is the so-called planar solution. So the electric field is pointing in one direction. I'm actually going to make it so that it's in the y direction. So E actually is equal to, let me rewrite this thing in here so that it's clear. Here, actually, we can do it here. E is equal to E as a function of x and t in the y direction. You will see soon why I'm going to make sure that the magnetic field better be perpendicular to it. So B will actually be, and I'm going to write it down right now, B, again, as a function of x and t in the k hat direction. So this is a wave that I'm going to, or not a wave, I'm sorry, I jumped ahead of myself again here and declaring what it was before even finding that it is. Okay, so this is a solution that is moving in the x direction. And I'm going to say that it's moving with a velocity c. At this point, I don't know what this c is. It's going to turn out to be the speed of light, okay? C is the speed of this wave, moving in this, moving the speed of this solution, moving in the x direction. That's basically all there is to it. So in other words, if I wait 1 second, this whole plane will move from this direction by c distance to here. So if I wait delta t amount of time, this whole plane would have displaced in the x direction by this amount. So that's my whole hope that maybe there is a solution of such nature. So that's really what we're trying to say in here. Okay. What I'm saying in here is the electric field will be the same on this plane, but not necessarily the same value on this plane. So it's the same value on a given plane, but it may be different from plane to plane. I will allow for that. I will allow for the electric field, and same thing for the magnetic field, both of them, to change from plane to plane, but on the same plane, both of them are the same value everywhere. So if I find E to be 10 volt per meter in here, this is also, I'm sorry, it should be black because I'm trying to argue the, so this should be also 10 volt per meter. And if I find the magnetic field to be, for example, 1 Gauss in here, this better be also 1 Gauss in here. Okay, so that is the whole thing in here. So that's the whole point. But it may be, if this were 10 volt, this probably could be 9 volt or 7 volt per meter. Okay, so from plane to plane, it may be different. So this is the so-called planar solution. So that's what the planar solution looks like. So E is the same on a plane perpendicular to the direction of propagation. When I say E, I meant also B too, okay? Both of them have the same thing, but they don't have to be necessarily the same. So let's explore this possibility for these equations. First of all, in terms of the divergence, I'm sorry, yeah, in terms of the divergence, the fluxes. If I take any closed surface in here, I'm going to use the green color for the surface. I'm going to take this surface in here. Obviously, what I'm saying, meaning in here is that this moves in the same direction. So that means the solution is actually made up of this planar fronts. Plane fronts, which means that E is some value in here, but E immediately is 0 and B is 0 after that front. In other words, there is a front that is moving. So if a light source, for example, from a source is going to take time for it to reach me. So while that front is moving, at some point, before that point, there is actually a value for the electric field and there is a value for the magnetic field. But after that front, before the solution reaches it, there is no electric field or magnetic field. So at that point, it's an undisturbed space. So this is the undisturbed, while this wave where this solution made out of these planes is moving towards it. At some point, when the plane solution reaches it, we're no longer going to have an E equal to 0 and B equal to 0 everywhere. So this is the only condition I'm going to have in here, okay? Because that is the direction of propagation. So the x direction better be undisturbed before that plane solution hits it. Otherwise, If we have solutions everywhere and they're the same, then these Maxwell's equations will become meaningless. They don't work that way. I mean, they will have an inconsistencies in them. So there better be places of the space that are completely undisturbed, okay? What I mean by space is vacuum. You don't even have to have anything in there because there is no mention whatsoever in these equations of any material that you need in that space. So when I say in here free space, I really don't mean any matter whatsoever. So that space that better be very calm before it's been hit by this solution. So that's what I mean by E equal to 0 and B equal to 0 before it. So if I take this surface now and calculate the flux of the electric field, for example. Okay, let's do the electric field for this solution, see if it works or not. The electric field, I assume to be in the y direction, as you can clearly see in here. It's in the j hat direction. So this area, this face is in the x direction, and the electric field is in this direction, is in the j hat direction. So the dot product of these two is 0, because that's what the flux is. The flux is the dot product of the electric field and whatever you're trying to find. So since it's the electric field in here, these two vectors are perpendicular, therefore the flux over this surface is 0. The flux through the other surface is the same thing as 0, because the surface is pointing this way, the electric field is pointing that way, and the dot product of these two perpendicular vectors is 0. How about this frontal surface? Same thing, it's going to be 0. This surface also is going to give me 0, because again, the electric field is pointing upward, and the area is pointing in the z hat, in the k hat direction. So it's 0. The same thing for the other area. All of these areas, they're perpendicular. So I have 4 areas, 4 faces of this geometry that are perpendicular to it. So they're going to give me 0. However, this area here, the electric field is in the j hat direction, and the electric field also is in the j hat direction. So the electric field and the area, both of them are in the same direction. And it's going to give me a value. So when I calculate, no matter what, it's going to give me a value. To go back to my 10 volt per meter, it's going to give me 10 volts per meter times this area. And let's say, for example, this area is 1 meter squared. So it's going to give 10 volt times meter, okay? But in the other side, in here, in the bottom side, the electric field is the same, as I argued before, in this entire plane. Okay? So it's the same value as this one. And the area is the same area, but it's pointing in the opposite direction. So if this was positive 10, this will be negative 10, and the two cancel. So the flux of the electric field is 0 in this area. If I extend my surface and make it outside, so that it encompasses this region where the solution did not reach yet, well, there is no problem there. The electric field is 0 anywhere there. Do you guys understand? So whether or not the wave front has reached that point or not, there is no flux in here for the electric field. So equation 1 is satisfied. So this solution works with equation 1, at least for the electric field, because the electric field has no flux in here everywhere, either because the electric field is perpendicular to the surfaces, or the contribution from different surfaces is the same but with opposite signs. So there is no net flux of E, period. So that is a check for equation 1. So this makes this equation work. So I'm going to put a check in here. So this equation works, because if it's after the plane solution front has passed, then in this case I definitely have an electric field, but it's the same everywhere on that plane. And it's perpendicular to 4 surfaces, which gives me 0 contribution for the flux. And it's the same value, but opposite sign for the 2 areas that point in the y direction. And they too add up to 0. So at the end, I check that value. The same thing also holds for this equation too, for the same reason. So let me redraw this because it became a little bit of a mess. I'm going to do the same thing for the so again, I have the y direction, I have the x direction, I have also the z direction, and again, this is a planar solution. It doesn't matter in here in this case. So the magnetic field now, the magnetic field is pointing the same everywhere in here, and it is the same value. That is the condition for the plane solution. They don't depend on y. In other words, on z in this case. So if I move from this point to this point, z has definitely changed on that plane, okay? And if I move from this point to this point, y also has definitely changed in this plane, in this solution. But I made sure that my electric field and both the magnetic field and the electric field do not depend on y and z. They depend only in the direction where I chose to be x, okay? So in this case, the same calculation as before. So if I take, again, any geometry, I'm going to make it simple in this case. So I'm going to take the same shape as I took before for my closed surface. So this is a closed surface made up of 6 surfaces, 6 faces. The magnetic field is this direction, and the surface is in this direction. So this is going to give me 0. In this, the same thing is 0, by the way, for the other one. The area is pointing this way, and the magnetic field is pointing this way, and that is a 90 degrees. So the area is in the negative x direction, and the magnetic field is in the positive z direction. So this is going to give me 0. Same thing with this one in here. The area is actually pointing in the y direction, and the magnetic field is in the actual z direction. So this is going to give me 0. The same thing for the bottom surfaces. So 4 surfaces also will give me 0 in this situation too. Okay? How about this surface? The one that is facing me here. That is going to be a positive value because I chose the magnetic field to be pointing in the z direction, and so is the area. Both of them are going to be the same value. If I look at the surface behind it, that is going to give me the magnetic field is still pointing in the same direction, same value, and the area is the same value, but it's pointing in the opposite direction. So if I find, for example, it doesn't matter in here how much flux I have, let's say, for example, negative 10 Weber, I will find the same thing in here, positive 10 Weber. So at the end, they will cancel each other too. So at the end of the day, the net flux in this case, no net flux for B, period. So that equation also checks. So far, out of the 4 equations, 2 equations are good, okay? So this solution works. I mean, it will not work if we do the following. If somehow I have an x component in here for this solution. If I have an x component for the electric field, for example, we have a problem because the value in here is not the value in there. Or actually, if I go way outside, the electric field is 0, and the electric field is some value in here in this direction. So I will have an offset. So in other words, you cannot have an x component for the electric field in the y direction, in the direction of propagation, period. So that means that this solution is really transverse. This is transverse. So I'm calling it wave because it's going to turn out to be a wave, okay? So this is a transverse wave. I want to ask you a question, guys, since we already are talking about waves now. Do you guys remember the wave equation that you did in physics 4A? How it looked like? That's coffee, by the way. You guys remember the wave equation or not? From your physics 4A? No? Okay, let me write it down, okay, because it's really something that is, you should have really, I mean, the derivation for it is really a little bit outside of the scope, but actually you could have done the derivation in physics 4A, and it's not really hard to do, honestly, okay? So let me share with you how the wave equation would look like. If you find, if you're working in any field, it doesn't matter which field that is, okay? And you find an equation of this form. I think this is how you should have done it in physics 4A, okay? you take a string and you disturb it, string, stretch string, and you disturb it, and you find the tension on one side and the tension on the other side, and you apply Newton's laws, and you will find that this bending of the string will yield this equation, basically, because now I have a string along the x direction, but it's moving up and down too in the time behavior. So you'll find that the way you bend the string has this expression in it, okay? 1 over quantity in here, which is v squared, times the partial of y with respect to t. And what you say then is that this equation is the wave equation. Anytime you're working on a problem and you find the constant positive in here. The reason why I put it over 1 over v squared, first of all, v squared is because it's positive, so that not to allow for it to be negative. The other thing also, it has to have dimensions of x over t, because no matter what the dimensions of y, in this case it's this displacement, so it's meters. In the case of sound waves, it's actually the amplitude of the it's the pressure, okay? So this will be in Pascal, or it could be the density of the air, which is in grams per cubic centimeter. So this, no matter what the unit for y, they will cancel. So this equation has the unit for y divided by meter squared is whatever that constant times 1 over second squared. So the unit times the unit for y also, because I still have a y upstairs. So the units for y cancel. No matter what the y is, they will cancel. And you will end up with, basically, if you invert this, in other words, you will have the unit 1 over v squared are the same as the units of second squared over meter squared. When you invert this expression, the unit 1 over v, units for v actually will be meter per second. So in other words, this is the velocity in terms of dimensional units. So this is the velocity, okay? When you solve the expression, when you write the equation from physics 4a, I'm trying to connect a little bit with physics 4a, you will find that it has two solutions: a function that moves in this direction, plus another function that moves in the opposite direction, okay? Here v enters this square root of this number, because this is a positive number. And you say this is a right, and you can argue actually why it's a right traveling wave, and this is actually a left traveling wave. So this equation in here is the wave equation. Once you see it, you recognize it, and you say, I know what that is, okay? This is a wave equation that has two solutions, one potentially traveling to the left, the other one traveling to the right. It doesn't matter. They travel with the velocity. These waves travel with the velocity v, the square root or the invert of this square root. So you take the square root and you inverse it, and you will find what the wave solution is. So this is from physics 4a. Does this ring a little bit of a bell? Anybody? Okay. Oh man, this. I'm sorry, it's okay, and everybody else. Okay, so this. Let's take it as a Bible, okay? Trust me. How's that? First of all, forget about physics 4a or anything else. Do you guys understand why it makes sense dimensionally that that number has to be meter per second? Yes or no? Okay, at least one person is responding. How about the others? The units of y cancel. Those partials, they're just operations. Okay, very good. And then the units of x better be meters, and the units of t better be seconds. And if you do the algebra back and forth, you're going to find it. So that's a meter per second. That's a key thing. That's what we want to find. Okay. The other thing also, probably could do it at homework, but I'm going to do it quickly since you guys don't remember it quickly from that class. Here. I'm going to call u, the letter u, that is, x minus vt. And I'm going to call w x plus vt. I'm going to focus on this guy first, okay? It's the same thing, okay? So what we do usually is the derivative of u, because u is a multivariable function now, okay? When I'm taking derivatives with respect to x, what I can say is I can take the derivative. So this function in here, for example, f, if I take its derivative with respect to x, I do the chain rule. So it's a derivative of u with respect, it's a partial, by the way, partial of u with respect to x times the derivative of that same function with respect to u. In other words, this function f of x minus vt, what I can say is a function of u. I made a change of variable. Now it's only a single variable. Correct? You guys see that? Between the connection to this one and this one. So this, I made the change of variable, I called u x minus vt. You guys see the algebra in here quickly? Yes or no? I need confirmation in here. I'm taking the f part of it, the right traveling side of it. Yes, no, maybe. I may have done it too quickly. Okay, I was trying to go. So, what I'm saying is the following. F of x minus vt, I'm going to assume it to be f of u. So u is, in this case, x minus vt. This is, by the way, standard in every textbook, and I think it's from Physics 4A also in the previous chapters. Okay, so this is now a single variable. So those partials don't mean anything. So for u, for the letter u, not for everything else. So when I say the df with respect to x, what I mean by is the du with respect to x times df with respect to u. You guys remember this from the chain rule? Yes or no? I need confirmations, please. At least somebody turn on the microphone to tell me that we're good in here. Because I can't see the chat at this point when I'm sharing the screen. I have to remove it before I can see the...
We're good.
Does this make sense, these two steps?
Oh, yeah. Yeah, makes sense.
Okay, so I'm going to find what this du with respect to x is. The partial of u with respect to x is just 1, as you can clearly see. The derivative of u with respect to x is just 1, because x is just, u is just x minus vt. So vt becomes a constant, so derivative of x is just 1. So that's clearly from there. So df, the partial of f with respect to x, is simply equal to the partial of, the derivative of f with respect to u. That's clear, okay? Now, if I take a second derivative, the second derivative of f with respect to x, then that's going to be the partial with respect to x, again of u, times the second derivative, because it's the derivative of f with respect to u, and this is also already 1, so this is going to be equal to the second derivative of f with respect to u. So in other words, the second derivative of f with respect to x is the same thing as the second derivative with respect of f with respect to u. So this is straightforward. I'm going to do the time dependent too. What I'm going to say in this case is the derivative of f with respect to time is the same thing as the derivative of u with respect to time times the derivative of f with respect to u. Again, we're making a change of variable in here, where u takes both x and t as all of the behavior of this function is inside u, okay? So, then in this case, but du with respect to dx is equal to, actually, with respect to dt is actually not equal to 1 now, is equal to minus v, as you can clearly see from here, okay? So I'm going to plug in this number in here, and I'm going to say this is equal to minus v df with respect to u. The last step in here is to take the second derivative of f with respect to t, and that's going to put another one. So it's going to be, again, du with respect to t times the derivative with respect to u of minus v df with respect to this guy, okay, to u. The minus v comes out to the other side. This would pull another minus v. Times minus v is going to be v squared. So this is going to give me v squared times df, d with respect to, it's going to be second derivative with respect to u. And this is exactly this derivative with respect to x. So this equation then says the second derivative of that function with respect to time is v squared, because minus v, and I have another minus v here. So it's going to be v squared times this. Did I write it wrong? Yeah. Times the second derivative with respect to, which is actually this one. The second of f with respect to x. This is exactly the same equation I wrote above. This is, I wrote it in the different order, but it's the same equation as this one. Here. Okay. So this f of x minus vt is actually a solution to this equation. That's all I showed in here. That if I take the function f of x minus vt and make this change a variable, I find that it satisfies this equation, this partial differential equation. So what I'm saying in here is the solution to this equation has this general form. It doesn't matter what that is. So it could be this function, okay, as a function of x and t. So I'm taking a picture of it. For example, if I take a picture of it, snapshot of it in time, this is how it looks like. So this is the function f. But it's moving to the right with a velocity v. So if I wait a few seconds later on, it's not going to stay in here. It's going to move and become this function. Okay? So it's moving. The profile of this function is moving in the positive direction with this one in here. Because if I take snapshot at equal to 0, if I wait a little later, the argument can be 0 at a different position, x equals to v times the later time. Okay? So this is in a nutshell the discussion. Please do not rely on this one. You really have to review this stuff because it's far more should be dealt with in physics 4a. Okay? But the point being in here, this is the right solution. Same thing actually with the left solution, except that instead of having a minus v in here, where is it? When we do the w changes, when I take the derivative with respect to time, I will have a positive v. So I'll have a positive v times a positive v is going to be a v squared in here. So both of them are actually solutions, whether the f or the g function. Okay. So having said that, if you're not math inclined, okay, and you're working your problems, you're an engineer, you don't care about where things are coming from, and you come up with this equation where y can be anything you're working on. It doesn't matter what that thing is, pressure, volume, it doesn't matter. Whatever you're trying to do, that y, it's partial derivative with a spatial variable. Oops. Control Z. Where is that second squared? With respect to x squared is a constant positive. That's the key in here. It has to be constant positive times the partial of this y with respect to time. Okay? You say this is a wave. This is the joke of physics. When you're doing joke of waves. Okay? So you see, when somebody's telling a joke and there is a punchline that they hit it, when you're doing waves and you're working your problem and you hit that point in your solution or your derivation and you find that, you say, I know what that is. You guys see that? That is a wave. It has this velocity. You guys understand? Because that's exactly what we're going to be doing right now. Does everybody understand? I know it's probably not funny and it doesn't make you laugh, but the point of it is this is a punchline. Once you reach that equation, you say exactly, I know what that is. That partial actually is the part of a big operator. It's the second partial with respect to time, with respect to space, is some constant positive. Time is a second partial with respect to time. Then you know, hey, this is a wave. Not only it's a wave, but I know its velocity too. You guys understand the point? Okay, at least one person is good. How about the others? Okay, so from now on, if you don't know where it's coming from, probably you don't remember it from physics 4a, or it was not covered in depth as it should have done, or some reason. Once you reach that equation, of course, if you take diff-EQ later on, especially partial derivatives, you're going to be sick of it because it's going to be really your starting point. You'll have far more than this. But the point being in here is once you reach that equation, you'll know what you're dealing with. Okay? So this is exactly what we're going to be headed to today. So we have checked 2 equations so far from Maxwell's equations. We checked equation 1 and 2 with this solution. I need to check the other 2 too. So I better find that. So I'm going to go back into my geometry again, back to my plane solution. So let me draw a line in here and see if I can find something in here useful out of them. So again, in this entire plane, the electric field is pointing in this direction. That is my proposal. And the magnetic field is perpendicular to it. And both of them are moving in a direction perpendicular to both of them. That is the x direction by choice. This is the y direction where the electric field is. This is the z direction where the magnetic field is. So this is my design, where the entire plane in here, the electric field is the same. So what I'm going to do is I'm going to move a distance x plus delta x. So this is happening at the position x. And this is now at the position x plus delta x. Of course, we're looking at only in space. We have a time variable in here. Time doesn't change in this case. So we have 2 pictures of the plane wave in here. And we want to find a solution that works for us for the other 2 equations. So what I'm going to do in here, I'm going to consider these 2 surfaces. So the first surface, I'm going to take a green color in here. So the first surface is this surface. Or this path, I should say. So this is the path. Path situated at a delta x from the starting point. So this width is delta x. Of course, I need a height. So I'm going to take a height a. That's a constant, a, okay? Doesn't matter. You will see that it doesn't matter. It's going to cancel out, okay? I'm going to find the circulation. Remember, the other 2 equations have to deal with the circulation. So first one, I'm going to start with the last one. The circulation of the electric field over this path, okay? Because I chose A along the y direction. So that's where the electric field changes from point to point, okay? So what I'm saying in here is, we're going to go, and I have to go counterclockwise to go in the positive direction. So I'm going to circulate in the counterclockwise. So I'm going to go in the bottom, this direction. I'm going to go up. I'm going to go to left and the top. And then we're going to come down, and we would have closed the path. In here, the electric field is always perpendicular. So what we're going to find in here, there is no circulation here. This is going to give me 0 for this portion of the trip only, because the path is in this direction and the electric field is pointing in the y direction. So this is perpendicular. So again, if I look to Maxwell's equations, I'm interested in finding the path, this part, in that portion of the integral, that is going to be 0. EDL is going to be 0. So here it's EDL is 0 because the 2 vectors are perpendicular to one another. The same thing. The circulation is happening in this direction in here, and the electric field is still perpendicular and has the same value everywhere in this path. So this is 0. 2. However, here it's not. The electric field is pointing up and has a value in this point, which is x plus delta x. Delta x in t. Sorry. And in here, in this entire portion of the trip, the electric field has a value ex delta t. But it's still pointing up, and the path is going down. So this dot product is going to be negative. Cosine of 180 degrees is negative. Cosine of 0 is 1. So that deals with the first part of the integral. So if I look back into this expression, this is the side I'm dealing with right now. Okay? So let's find that. So I'm going to label them 1, 2, and 3. So I have 1, 2, 3, and 4. For 1, I have 0. For 2, I have minus E evaluated at x and t times, and it's the same E everywhere. Remember? The whole point of it, E, at least on this plane, it's the same E everywhere. So it doesn't matter if I find it in here or in here. So when I integrate a constant, so it's a constant times this A. For 3, it's 0. For path 4, it's actually a positive number, E, but this E is a different point in space, EX delta A plus and dt times A. So this whole thing, on the left-hand side, we have this expression, which basically says A times E evaluated at these 2 points minus E evaluated at this point must be equal to something. So what I did actually, if you guys notice, from this equation is to just look at this part. We need to deal with the second part now. The time derivative of the flux of the magnetic field over an area enclosed by this path. So here is the area enclosed by that path. Okay. Obviously, I have to find B. B is pointing this way, coming out. And the area is also coming out, okay? Because as I am going this way, okay? As I am going counterclockwise here, the area is coming towards me. And the magnetic field that shows it also towards me, okay? So, if I do that, then the area now, I know how much it is. It's A times delta X. That's how much the area is. And the only thing that changes in this area is the magnetic field, okay? So I'm assuming that the delta X is so small that there is very hardly any changes, because we're going to take delta X to go to 0, by the way. So delta X ultimately is going to be 0. So you're worried, okay, you're saying the magnetic field in this point may be different than the other point, but we're collapsing these two areas at the end, so we don't worry about that. So we're going to take the limit when delta X is equal to 0. So think of it as B average if you wish, okay, because there is a problem now with B. And that's the only thing that changes with time now. So what I'm saying in here is this expression says, let me look at the Maxwell's equations. It says minus the time derivative of B times the area. Says minus the time derivative. Remember now, I'm sorry, the time derivative B has depends also on other things. So we cannot do a straight derivative now. Times the area, and the area is A times delta X. Cancel the A from both sides. That's why the A did not matter how much we take it. We just took an arbitrary A in there. So at the end, it did not matter, because that's just our Empyrean loop that we chose it, and it should not matter at the end of the day, and it did cancel. It's not part of the physical problem, just to help us find the solution. So now we have an equation. Let me rewrite this equation. E evaluated at X plus delta X, and T minus E evaluated at X and T divided by the same delta X equals to minus the partial of B with respect to time. If I take delta X goes to 0, this expression goes to 0, this also goes to 0, so the difference in here goes to 0, and this is the limit of the function, in this case, of X plus H minus f of X divided by H, the limit of this expression when H goes to 0. This is nothing but the derivative of f with respect to X in that point. So the same thing in here, except now I'm dealing with a function that depends on two variables. So this is going to be the partial of E with respect to X is equal to minus dB with respect to time. So this is equation 1. So this equation now is what this equation looks like. Okay. Now we have to work with the last equation, which is this one. This equation, then, we're going to take a different path. We're going to take the same two planes, by the way. Okay, I've been doing it in black. Let me be consistent a little bit. So, again, I'm taking two planes now. One situated at point X at time t, and another one situated at place X plus delta X and t. So the time is the same. So this is a picture, snapshot at the same time. So what I'm going to do now, I'm going to take again, this is the x direction, this is the y direction, and this is the z direction. And this is the plane, the side that we're going to do, because now we have to deal with the changing magnetic field in the z direction. So again, this distance is delta x. Remember, delta x ultimately going to be 0. And this depth is going to be b now, okay? And it's on the plane, by the way. And I'm going to go back to an equivalent point on the second plane, and this is b also, okay? On this loop now, remember, I'm trying to find this integral, BDL. So I will have a portion in here where the area is this way. I mean, the path is this way, going from here to here. Again, it has to be counterclockwise, and to here, and into there, back into here. So again, we can label it by 1 and 2 and so on and so forth. The magnetic field is pointing into the z direction as we chose it. The path is normal to it, so this gives me a 0 contribution. The same thing, the magnetic field is pointing this way. The path is actually going this way. This is going to give me a 0 contribution. The magnetic field in this point, situated at x plus delta x and t, is actually coming out, whereas the path is going in. But in here, it's coming out, whereas the path is also coming out. But this value is in the position x and t, and this value at the position x plus delta x and t. So that's the only two differences in here. So on one side, I'm going to have a 0 on both sides, which I'm not going to bother with at this point. Hopefully, you guys got it from the previous example. In here, I'm going to have a minus b evaluated at x plus delta x and t times the path b, because the electric field, the magnetic field is the same everywhere in here. So it's going to come out. So the only part of the integration is just going to be b, plus this is in the same direction, so it's going to be positive, b at x and t times b. This is on one side. This must be equal to the time derivative. Okay, I have mu naught epsilon naught first, I have to include in here, times this area. This area is b times delta x, b times delta x, and times the last part in here is the time derivative, because this expression has a time derivative too. It's the rate at which the flux of the electric field is changing. So this is going to be the change of the electric field over that same, and the same argument holds true for the fact that we're going to take an average. Ultimately, delta x is going to be to 0, and we don't have to worry about that. So this is be canceling. So what I have now is this expression now, minus b evaluated at x plus delta x and t, minus b evaluated at x and t, divided by delta x is equal to mu naught epsilon naught times the derivative of e with respect to time. There is no second derivatives whatsoever. This again, in the limit that delta x goes to 0, this whole thing is just derivative of b with respect to x. That's the definition of the derivative. So this minus db over dx is equal to mu naught epsilon naught dE with respect to t. So this is the second equation that we ended up with. Combine this equation with the previous equation, this one. So what I'm going to do in here, I'm going to take the derivative of this expression with respect to x everywhere. So the first equation becomes the second derivative with respect to x is minus the mixed derivative with respect to x and t. So what the first equation says is the second derivative of e with respect to x is just minus the mixed derivative of b. Same time, same thing. I'm going to actually take the derivative now of this expression with respect to t. And this will give me the mixed derivative of b with respect to t with a negative sign in front of it. So minus the mixed derivative of b with respect to x and t is equal to mu naught epsilon naught times the second derivative of e with respect to t. So mu naught epsilon naught times the second derivative of e with respect to t. Now, having said that, these two equations, this is the same mixed derivative, by the way, with a negative sign. That means this guy and this guy are equal. That means that what we have found is a wave mu naught epsilon naught, the second derivative of E with respect to time. So the electric field is actually a wave. So E is a wave. You see my point earlier? Once you see this equation, you say, I know exactly what that is. That is a wave, where C, the one that I mentioned earlier, is nothing but 1 over the square root of mu naught and epsilon naught, because this is 1 over C squared. So when you invert it and you take a square root, because mu naught and epsilon naught are actually both positive numbers. As a matter of fact, I know mu naught equals to 4 pi times 10 to the negative 7. And I know epsilon naught, if you guys remember from the discussion before, way back, times 1 over 4 pi epsilon naught is 9 times 10 to the power 9. So if I divide that, so it's going to be 9 times 10 to the power 9 divided by 4 pi. So if I multiply this 2, no, this is wrong. Epsilon naught is not like that, okay? Let me remind you of what we were doing, okay? So 1 over 4 pi epsilon naught is equal to 9 times 10 to the power 9. In other words, epsilon naught is 1 over 4 pi times 9 times 10 to the power 9, okay? Did I do it right? Yeah, I think that's correct, okay? So if you multiply this 2, the 4 pi cancels, and 1 over is going to be 9 times 10 to the power 18, and C, 10 to the power 16, because 7 plus 6, 9 is 16, C will turn out to be 3 times 10 to the power 8 meter per second, which is exactly the speed of light. The same thing, by the way, I did this. We could have done it differently, okay? We could have gone to this expression, the first one, and take instead the derivative with respect to t instead. If we take the derivative, here we will have the mixed derivative of E with respect to x and t, and here we'll have the second derivative of B with respect to time. And the same thing in here. If we did this derivative instead of with respect to t, we would have done it with respect to x. Here, we will have the second derivative with respect to x, and in here we'll have the mixed derivative, and the same thing will be held at the end for the magnetic field too. So the second derivative of B with respect to x will turn out to be mu naught epsilon naught times the second derivative of B with respect to time. So in other words, I proceeded by finding the equation for the electric field by eliminating, because these equations, both of them are mixed between E and B. So we had to get rid of one of them and using this trick of taking the cross derivative, the cross partials, and then at the end, we're left with just a single equation for both the electric field and the magnetic field, and both of them are that of waves. And we know what those waves are. They travel with mu naught epsilon naught. This, of course, what Mr. Maxwell has reached when he found his equations, and he was puzzled, is light really waves? Because it looks like the speed of light is the speed of these things, the electric field and magnetic field. It took Mr. Hertz later on a lot of work and then experiments and things like that to show that indeed those are waves, because he was able to produce an electric field and magnetic field with an antenna on this side and go and measure the other side and find the same basically expression that Mr. Maxwell has found. And not only that, but the speed is that of the speed of light, and this whole spectrum of light is just a small fraction of the entire thing. So if you look at the entire spectrum, this is just a portion of a big spectrum. It starts with very, very short wavelength, namely lambda is very small, to very long wavelength, okay, where lambda is very large, okay. In between them, the spectrum for the visible is somewhere in here. So you have the red in here, you have the red on this side, and you have the violet on this side. And this is the visible light, visible. On this side, you have the UV. On this side also, you have the X-ray. and you have the highly energetic gamma rays. Okay, so this is high frequency. And on this side, you have the microwave, the infrared first, IR, and then you have the microwave, and you have the radio wave. Radio wave like your cell phone and telecommunications and things like that. Okay, and you have even far longer wavelengths. So this is the solution to Mr. Maxwell's equations. It turns out to be waves. Okay. And this plane wave, a planar solution, is a solution to it, okay? So this is basically, so if you ask me what is the solution, anything of this form, f of x minus ct now, where c is the speed of light, is a solution. So you could have actually standing waves, and that's actually what Mr. Hertz did actually early on with another wave, I'm sorry, G. Always we do G for so you could generate standing waves. That's exactly how he did. So a particular solution of interest, we end at 205, don't we? Or 225? I don't remember now. I'm lost, especially after this break. Can anybody remind me of the time when we were supposed to end the class? Could look up, but I don't want to. Okay, we're gonna finish it at 205. Okay, regardless. Okay, I made a decision unless you guys have. Okay, because we have a lab later on too. Does this sound good, everybody? Okay. Sebastian, did you say okay to this one, or was it previous? Okay. I'm not sure. Okay, very good. So, okay, I want the point of the discussion to be that of the wave, okay, equation. I want you to really remember that. So I want it to be part of the discussion today, that the wave equation is the one that I mentioned. You can put it in your own words, but that is really your ha-ha moment, whether you're doing, I know it's not funny, but that's how we say it. It's the punchline of waves. So please remember that, okay? So that's going to be part of the discussion today. And that's the last things we're going to have is this discussion. After that, there will be no more discussions, okay? I mean, you could have discussions anytime you like, guys, okay? So don't say that we are done, I cannot ask questions. Please do ask questions all the time. So this also checks, by the way, we checked it right now, okay? So all of the equations, they lead to this form, okay? So the other type of waves that I didn't mention are the so-called harmonic waves, okay? Harmonic waves are just a special case of these things in here, okay? Because all they are is just a cosine and a sine wave. So what I'm going to say in here is E is some maximum value times the cosine of some kx minus omega t, or if you wish, some k times x minus ct. So you could take this and write it as E max times the cosine of k times x minus ct. So once I write it in this form, I know exactly what this expression, in other words, what this C is related to. C is simply equal to what? Omega over K? Kc is equal, yeah, omega over K. So this will become what is known as a dispersion law, okay? Of course, the magnetic field B is also equal to B max times the cosine of the same K times x minus ct, or B max times cosine of kx minus omega t. So this K and omega are related to one another through this expression right away from the get-go, okay? And we can plug it into Maxwell's equations and it will make sense there. As a matter of fact, if you take the second derivative of E with respect to time, so the second derivative of E with respect to time, the first time is going to pull a minus omega times the same stuff, but you'll have a minus sign in here. And then the second time it's going to pull another minus omega, and it's going to have the sign becomes a cosine. So it's going to pull a positive omega squared times minus E max times cosine of kx minus omega t. Please verify this. It's not hard to do. all you have to do is take the derivative twice and it's going to pull a minus, okay? And the second, it's going to have that minus omega. This partial derivative of E with respect to time is going to pull, the first time it's going to pull a positive K from it, but the cosine becomes a negative sign. The second time it's going to pull another positive K, so it's going to be K squared times a minus the same thing, but the derivative of the sign becomes a cosine. So basically what this expression becomes is K squared times minus again E max times cosine of Kx minus omega t. Okay, this is multiplied by mu naught C naught, mu naught epsilon naught. And this is exactly if we multiply it by 1 over c squared. So what this expression says then is omega naught squared, I'm sorry, did I do, this is x, I'm sorry, this is x. So let me write these things again, okay? So this is x, and this, therefore this is k squared times minus E max times cosine Kx minus omega t is equal to mu naught epsilon naught, which is 1 over c squared, by the way. I should have really stopped using this symbol, times omega squared times the same stuff, which is minus E max times cosine of Kx minus omega t. This thing cancels all the time, no matter where you are in space and where you are in time. It's the same thing that cancels. E max cancels, the minus cancels, and then what you are left up with in this case is K squared is equal to omega squared over c squared. Remember, c squared is actually equal to 1 over epsilon naught mu naught. So, of course, k and omega are both positives. That's how we take them. So the square root of this expression then becomes k, or kc is equal to omega. This is the expression that I argued earlier is the dispersion law, okay? Omega equal to kc, or c is equal to however you're going to write it. Omega is 2 pi over t, or 2 pi times f. That is what omega is. The angular frequency. Because this is a cosine, this is a harmonic wave function. Okay, we still have 1 minute. Okay, allow me to finish that. And then k is what is known as the wave number, 2 pi over lambda. So if I plug this expression in here, so it's going to be 2 pi over lambda times c is equal to 2 pi times the frequency. Cancel this 2 pi from both sides, and c, the speed of light, is lambda times f, lambda times frequency. So we're arriving slightly to a little bit more advanced stuff now based on how this wavelength, lambda, is related to this frequency f of the solutions, okay, for this, the electromagnetic spectrum. So that's basically, in a nutshell, how this solution works. Now, there is another important relationship that I didn't derive, and we're going to get to it very quickly, and that is taking any of these expressions, it doesn't matter which, okay? I'm going to take this one. The first one was easier. Where is it? This one, okay? We're going to take the derivative of E with respect to x and take the derivative of B with respect to time and make them equal to one another, because that's basically what this equation is saying. Okay, the derivative of E with respect to x. That's what this expression is. Let me rewrite this expression in here. So, where is it? I'm trying to find it first. Yeah, dE with respect to x equal to minus dB with respect to time. So, let me write with the red pen. So dE with respect to x is equal to minus dB with respect to time. dE with respect to x is just k times this whole thing with a negative sign. So it's going to be k times E max with a negative sign, by the way, times sine of kx minus omega t. That's one side, equals to minus this minus, okay, dB with respect to t. So take the derivative of b with respect to t. So when I take the derivative of b with respect to t, I'm going to pull a, first of all, there is a minus in here. There is the minus coming from the cosine, and there is a minus from this expression itself. So there are three minuses, so I'm left with only one minus. So hopefully you kept track of these minuses. And I have a B max times omega, B max. When I take the derivative of the cosine again, it's going to be a minus sign. So I have three minuses, and I'm left with a sine of kx minus omega t. So again, the sinuses cancel, the minuses cancel, and I'm left with B max equals to k over omega times E max. And k over omega from this expression, what is it? The one that k over omega is 1 over c, by the way, from this expression. K over omega is 1 over c. So B max is equal to E max over c. This is a very important relationship that we need to get to it. Okay, it's very, very important that we have to get to this expression, and that is the intensity of the magnetic field is always 1 over 300 million times less than that of the electric field. Okay, so because the speed of light is 300 million meters per second. Okay, so that's why our eyes and most of the antennas in daily applications, they deal with the electric field. They don't care very much about the magnetic field because it's too weak to be detected with instruments. So your eyes are far more tuned to seeing light with the electrons in those sensitive portions in on top of the retina that start to move back and forth, that are excited by the electric field that is hitting your eyes. Right now you're looking at the screen. So that is because the E max is very, very big compared to relatively speaking to the magnetic field. That's why we were not tuned, and even our devices on a daily experience that we make for antennas, for telecommunication and everything else, we deal mainly with the magnetic field. So this is an important relationship. This is a so-called dispersion law. And this is how the magnetic field and the electric field are related. This is critical to your homework. This is critical to your exam 4, that is. Okay, I know I took a little bit more of the time that is allotted. So I'm going to finish here, and then we're going to meet for the last lab, which is going to be non-linear electronics, and we're going to have it briefly, and then we're going to meet on Wednesday to finalize everything, getting the pointing vector and everything else. Everybody on board? Yes? Okay, at least one person is on board. Very good. Okay. See you guys. Okay, 2. Okay, see you guys on a little bit, okay? Bye. Okay, more people. Thank you. Let me stop the recording.